everyone, so today we are going to be looking at the KC Maths Mock 2021 Integral Calculus. So it says perform the following integrals. Roman 1 says the integral from 0 to power 4 of 1 plus cos 4x over cot x minus tan x dx. Roman 2 says the integral from 1 to e squared x to the negative 1 in x dx. Roman 3 says the integral from 0 to 4 absolute value of x minus 2 respect to x. Okay guys, so the first part of the question says that the integral from 0 to power 4 of 1 plus cos 4x over cot x minus tan x dx. Okay, for us to do this integral, we can basically just simplify this function inside here until we get to a particular function that is clearly integratable. So we want to start with the numerator, so we just come over here. The numerator is 1 plus cos 4x. Now you realize that just come over to this last bracket here. Cos squared x is half plus cos 2x over 2. Now if I multiply all through by 2, you realize that my 2 cos squared x will be equals to 1 plus cos 2x, right? Now if 2 cos squared x is 1 plus cos 2x, then 2 cos squared 2x will be 1 plus cos 4x, right? Basically there's the double angle of this guy. You realize that in place of 1 plus cos 4x, we can conveniently put what? 2 cos squared 2x. Are we there? From this identity like that, and then using the double angle of 2x. Now if we come in the denominator, cot x is the same as cos x over sin x. Tan x is basically sin x over cos x. And then if we go ahead and then we simplify that expression by looking for the LCM in this denominator, which is basically just going to be sin x cos x, and then simplifying everything, you realize that we're actually going to have 2 cos squared x 2x cos x sin x, because that's going to be the denominator down here, the LCM of the denominator. And then when this denominator therefore will completely simplify to basically cos squared x minus sin squared x. Now our cos squared x minus sin squared x, remember that is cos 2x. Then of course the numerator just stays the same. Then we can come over and say that, but this 2 here, this 2 right in front here, times this cos x times sin x is basically sin 2x. So we are basically left with cos squared 2x over cos 2x, which gives us cos 2x, and then sin 2x, right, which is this. Now we're going to call this guy, this integral, which is basically, now because we're simplifying this function inside here, now that function simplifies to cos 2x sin 2x. It means that the integral of the whole of this function is basically the integral of cos 2x sin 2x. So let's call that integral I. Now we can come down and say, but then I can actually multiply this guy by 2 and I put a half out here, so that I have 2 cos 2x sin 2x dx, so that my 2 cos 2x sin 2x becomes what? Sin 4x, because 2 cos theta sin theta is basically sin 2 theta. So our theta now is 2x, so we can just basically have sin 4x there. So I'll basically be integrating sin 4x from 0 to power 4. Now you realize that if I integrate sine, I basically have negative cosine. So since I'm integrating sine 4x, I'm going to have negative cos 4x. Then I differentiate this angle here, which is just 4. I divide by that. So I now have my negative half, which comes out here, divided by cos 4x over 4. Then the integral from 0, the limits from 0 to power 4. We substitute in those limits, and then we have, of course, my negative half is out here. Upper limit give me this, and then my lower limit, and then that simplifies to half square units. Perfect. So I hope that you understood this first part of the integral. We can move on to the next. Okay, so the next part of the question says that integral from e to e squared of x to the negative 1 in x with respect to x. So what students are usually tempted when they see problems like this, right? It's a product function. One function is actually logarithmic, the other one is algebraic. Students are usually tempted to go to use the method of integration by part, where you actually can let this ln x to just be your u, and then you go ahead to look for du, which will just be 1 over x dx, and then you let this x to the negative 1 to be your dv, and then when you integrate 1 over x, you basically have ln x, right? Now you realize that if you use that by part formula, uv minus integral of v du, the integral of v du would basically go back to the same integral, right? So it gets you in circles and in circles and in circles. All right, so what we are going to do here is that we recognize that this function is actually a product function, that we can manipulate in a very strategic manner. So again, I can write the x to the negative 1 as 1 over x, ln x respect to x. That's just my integral, nothing has changed. But then I realized that if I differentiate with respect to x ln x, it basically gives me 1 over x. So I can actually multiply throughout by delta x, so that I have my d of ln x to be 1 over x dx. So you now realize that in the place of this integral, whenever I see 1 over x dx, I can just put my d of ln x. So 1 over x dx is d of ln x. So I have the integral from e to e squared of ln x, d of ln x. Now when I'm changing this integration parameter, I have to change this integration limits, because initially it was with respect to x and the limits were e to e squared. Now I'm changing the limit, the parameter from delta x to d of ln x. So what I have to do here is that I also come and change this limit. Now if my x is e, what would ln x be? Ln x would just be 1. If my x is e squared, my ln x would just be 2. So my upper limit now is 1 and my lower limit now is 1 and my upper limit is 2. So I can go ahead and integrate ln x with respect to x. It's just the power rule of integration. It's like integrating x with respect to x, which it means that you just have x squared over 2, right? So I basically have ln x all that squared over 2. So my limits from 1 to 2, and then I can substitute those inside, and then I have, okay, my ln 2 squared unit. So that is how you do that integration. Okay, so the final part of the question actually says the integral from 0 to 4 of absolute value function of that respect to x. Yeah, so we're calling the integration I. Now this is GCE 2003, and I think it also came in 2008, something like this. All right, so let's just see how we can integrate absolute value functions. Now again, you can just treat those functions as piecewise defined functions on various domains. So your general integration is from 0 to 4, but then this guy actually has its particular domain. He has two possible functions with each having its unique domain. So we're going to define that function. Absolute value of x minus 2 is basically x minus 2 for all x minus 2 greater than or equal to 0, right? If that x minus 2 itself is greater than or equal to 0. So you realize that in that case, it implies your x is greater than or equal to 2 here. Now this absolute value function can still be the negative of this, which is basically 2 minus x. That is for all the function itself being less than 0. That implies that x has to be less than 2 for the function to assume this particular unique function, and the absolute value function is going to just be x minus 2 over this particular domain. Now you realize that we can now therefore integrate the function from 0 all the way to 2. So we are splitting the domain, right? Because we're integrating from 0 to 4, but the function assumes two different domains over this particular interval. So we'll first of all integrate the function from 0 to 2, which takes this particular function, and then we integrate it from 2 to 4, which takes this other function. So again, that's what we've done. From 0 to 2 is 2 minus x, and then from 2 to 4 is this other function, x minus 2 respect to x. So we go ahead and then we integrate this 2 minus x, which basically gives us 2x minus x squared over 2, the limits from 0 to 2, and then we integrate this guy, which is just x squared over 2 minus 2x, limits from 2 to 4. So we substitute in our limits, and then of course we have that, and our I is just 4 square units. I think that was very easy. So the trick here is just for you to understand that absolute value functions are defined on unique intervals, so you can treat them as piecewise defined function, each part of function having its unique domain over which you can find its integral, right, and then sum them up. Alright guys, hope you enjoyed the video. We have come to the end of our series today. If you want us to solve more problems on any particular chapter in advanced level, please leave your recommendations or comments below in the comment section, and then please smash the like button if you enjoyed the video, and then share the link to your friends, to your classmates who can also use this platform to prepare for their GCE. Thank you so much. Hope to see you next time.